Welcome to Catalysis. So, we've seen already that increasing the temperature increases the reaction rate. But sometimes we can't increase the temperature, or not enough to get the reaction rate that we want. So, one example of this is that cells can typically only survive at relatively narrow temperature ranges. In the human body, if temperature drops below the low 90s in Fahrenheit, if your body temperature gets below about 90 degrees, you're going to die. You have hypothermia. You lose consciousness before you even reach a body temperature of 90 degrees. And if your body continues to drop, you'll die. Again, on the high temperature side, if your body temperature gets over about 108 degrees Fahrenheit, you also die. Your body just can't handle it. So you really only have about a 20-degree temperature swing, and even in there, you're not conscious for the last 2 or 3 degrees on either end. So really, and note, if you've ever had a fever of 102, 103 degrees, you may remember that you felt really bad. Now, of course, you're sick, but just the fever itself causes your body causes you to feel really bad. You may start to get delirious if your fever gets really high. So our bodies really can only operate in a very narrow temperature range. The chemical reactions that occur in our bodies get really messed up outside that range. So our bodies need to have some way of adjusting the reaction rates without using temperature. So in these sorts of situations, we can use catalysts, or in our bodies, we use enzymes. Enzymes are biological catalysts, basically. So a catalyst is a substance that speeds up a reaction without being consumed. Note that there's really no difference between a catalyst and an enzyme, except that an enzyme is used in a biological sort of situation, and a catalyst is used in a non-biological situation. So a chemist is likely to call it a catalyst, a biologist is likely to call it an enzyme. So catalysts work in one of two ways. They work by either lowering the activation energy or by increasing the likelihood of the collision orientation leading to reaction. So if the activation energy is lowered, then a larger fraction of our collisions will have the activation energy and our reaction rate increases. So if we look here, we have our reactants, we have our products, we have two different ways of getting from our reactants to our products. Same reactants, same products. One way is our uncatalyzed reaction. So that's sort of the pink curve, the top one. We have high activation energy. Remember, the activation energy is the difference between our reactants and the transition state, sort of the peak, the top of the hill. The other reaction here, the other pathway that we have, is this catalyzed pathway. And note that that activation energy is significantly lower than the first, the uncatalyzed reaction. Now remember that we have a range of energies in our molecules. They have a range of speeds, and so if the molecules that are coming together are moving very, very fast with respect to one another, they have lots and lots of energy. So they have maybe a kinetic energy when they collide that's up here. In either way, whether it's catalyzed or uncatalyzed, those molecules are likely to react if they're reacting with the right orientation. But if we have some slower moving molecules, if the molecule has, say, this much energy, that molecule cannot undergo the uncatalyzed pathway because they'll get partway up the hill and they'll have to go back down, as if you were, say, playing miniature golf and you hit the ball sort of lightly and it rolls up a hill towards the hole and then it rolls back towards the starting point. It needs to have enough energy to make it up that hill. Now, just like in miniature golf, if we lower the hill, we're more likely to get our ball up the hill. With our reaction, if we lower the activation energy, more of our molecules will have that much energy, so more of them will be able to go ahead and proceed. So with our catalyst, if we're lowering the activation energy, we're increasing the reaction rate. Note that if we go the other way, if we have an increase in in activation energy, then we don't have a catalyst, we have an inhibitor. This thing is causing it to be less likely that we have our reaction proceed. So, again, if we have our uncatalyzed reaction, we have some activation energy. If we move that energy farther to the left, we have a larger fraction of our molecules that, when they collide, can go ahead and react. So that was the first way, lowering the activation energy. The second way of increasing our reaction rate is to increase the likelihood of the collision orientation that leads to reaction, right? So remember that we need to have some orientation or some set of orientations during the collision in order to have our reaction take place. If we have our molecules collide in some unfavorable orientation, they'll collide, and then they can't form the bonds that they need to form, and they separate again without reacting, even if they have the activation energy. So if a collision is more likely to have the required orientation, then the reaction rate increases. And usually this is done by adsorbing the reactant or reactants on a solid surface. So often when we put molecules onto a solid surface, then they're held in some particular orientation on our surface. So if they're held with, say, one end of the molecule down, and then those molecules can come and strike each other side to side. If this occurs, if now we're fixing our molecules to strike each other side to side, if that side to side orientation is able to lead to a reaction, we've essentially eliminated the possibility that we have sort of the wrong end of the molecules striking each other. If we're able to do that, then by adsorbing our molecules onto our solid surface, that means that now we're able to increase the likelihood that when the molecules collide, they lead to a successful reaction. Here's one example of a catalyst. We have our catalyst here. These are the surface here in sort of gold. And if we take ethylene and hydrogen, so we've got the ethylene here, we've got two hydrogen molecules there. We put our ethylene onto the surface. What happens then is down here, so when we put the ethylene on the surface, and we put our hydrogen on the surface, it turns out that the hydrogen can split apart. And partly this is because when we put the hydrogen molecule down on the surface, we're weakening that hydrogen-hydrogen bond, which makes it easier to break. And now we're able to have hydrogen atoms move around on the surface, and when they then collide with our ethylene molecule, they can then react and produce our ethane molecule, and our ethane molecule then desorbs off the surface. Our two hydrogen atoms here that are left over may then collide with one another and leave the surface, or they may stay there for another ethylene molecule to come in and collide with that. So there are two types of catalysts. There are homogeneous catalysts and heterogeneous catalysts. A homogeneous catalyst works in the same phase as the reactants, which is then usually in an aqueous solution, although it may be a liquid form. So this is something like chlorofluorocarbons catalyze the destruction of ozone, leading to the ozone hole. Note that this happens in aqueous solution. It may happen in aqueous solution, it may happen in the gas phase, but whatever it is, whichever phase it is, it's happening together in the same phase. You don't have a surface that you're putting molecules on. Like in the last example, that was an example of heterogeneous catalysis. Again, homo means same, hetero means different, so homogeneous means same type, heterogeneous means different type. So we have, in this, heterogeneous catalysts work in a different phase than the reactants. It's usually a solid catalyst and gaseous, sometimes liquid reactants. So one example of this is the catalytic converter in automobiles. This is a heterogeneous catalyst. You have a bed of usually an oxide support. You've got some platinum and rhodium and perhaps some other metals in there as well. And then you have the combustion gases from the engine. You've got nitrogen oxides that you need to decompose back into nitrogen. You've got some uncombusted hydrocarbons, some uncombusted gasoline, or only partially combusted, maybe some carbon monoxide, some other small hydrocarbon species that you then need to oxidize to form carbon dioxide. And so these gases adsorb onto the surfaces of the platinum and rhodium particles. The reaction takes place on the particles, and then the products leave the surface. So again, here's sort of a big blown up picture of the catalytic converter in your car. You've got the uncombusted fuels coming in. They pass over the catalytic substrate here, the bed of platinum and rhodium particles on this oxide support, which means that they sit on the surface for a while, and then they react, they come off the surface, and they leave as carbon dioxide, water, vapor, nitrogen. So that was catalysis.